Welcome to Math with Malia. Today we're doing Savvas enVision Algebra 1, Topic 3, Lesson 6, Analyzing Lines of Fit. After this lesson, you will be able to find the line of best fit for a data set and evaluate its goodness of fit. We've got some new vocabulary words to use, and we will be using our graphing calculator, so make sure you have your graphing calculator. For the Explore and Reason, we have this scatter plot, and it shows the number of people that go to the beach for the first 6 days of July. And the temperature is the input, or on the x-axis. So degrees above 80 degrees Fahrenheit, and then the number of people that are at the beach. And the head lifeguard compares these two linear models, so we can see these two equations, g of x and h of x, are given. They're slightly different. The rates are slightly different, 13 versus 12. And then the starting temperatures are slightly different also. Okay, so remember these are in slope-intercept form, y equals mx plus b, where m is our slope and b is our initial value. So we're going to copy this scatter plot on another grid and try to graph the linear functions. So we want to basically draw the line. So if we're starting at 25, that would be right here, and then it goes up 13 and over 1. So we could do 13 times 5. So we would draw our two lines. So if we went over 5, that means we would go up 13 times 5, right? And do the same for 12. So you can do it in two different colors, and we're going to compare those two lines. So here are the two graphs for each of those. G of x is in red and h of x is in blue. And you can see that the red line for g of x, it goes through most of the points. Most of the points are on the line or touching the line. We just have this one point here that's a little bit below the line. For the blue line, h of x, that one's a little bit above, this one's above, seems to touch that one doesn't touch. So a couple more are off the line than the red line. So the red line only has one data point that is not touching the best fit line. The blue line for h of x has two that are not touching the line. So which one do you think is the better line that fits that data set? Well, we could probably say g of x, because the red line seems to touch or go through most of the data points. Part B asked about a reasonable domain for each function. Remember, domain is talking about our x value, okay, our input values. So what is a reasonable range for our domain? Well, we see our data points go from 0 and nothing is past 20. So we could say our domain, our x values, need to be in between 20 and 0. So greater than or equal to 0 or less than or equal to 20. That would be a reasonable domain for this data set. Example 1. What is the equation of the line of best fit for the data in a table? So we're looking for the best fit line. In the previous lesson, we practiced drawing trend lines through the data, and we wanted to make sure our trend line balanced out the data points, that there was approximately the same number of data points above the line as there were below. And we could draw that slightly different ways. We can use our graphing calculators to find the best trend line, or the best fit line, the one that matches the data most accurately. And we use what's called a linear regression. So the first thing we're going to do is take our data table and we're going to put them into our lists. So your x values are going to be your list 1 in general, and your y values will be your L2. And then we're going to do what's called a linear regression. So on your graphing calculator, we're going to go to Stat. So hit the Stat button and then Edit, option number 1, and you can see it pulls up the lists. So for L1, we're going to type in our x values. Hit 1 and then Enter, and you can see it automatically scrolls down. So then we're just going to hit 2, Enter 5, Enter 8, Enter 9, Enter and 17, Enter. So there are our x values. Arrow over to list 2, and this is for your y values. So you're going to enter 30 and 55, 75, 120, 145, and 250. So we have our data in our lists, and to do the linear regression, you're going to go to the Stat button again, over to Calc, and you can see option 4 has LinReg, which stands for linear regression, and you can see it looks like ax plus b. That looks an awful lot like y equals mx plus b, so that's showing us it's going to be in slope-intercept form. Hit enter, and we want to make sure that our x list in our table is pulling from list 1. So that's just saying your x values are pulling from list 1. Yes, that's what we want. We want our y values, our y list, to pull from list 2. And then you can just hit enter, 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 calculate, yes. And then you get this screen. It's showing you again at the top that we're in slope-intercept form, y equals ax plus b. Looks like a is going to represent the slope. And then it gives you the values for those variables. A, or the slope, is going to be 13.55 and some more decimals. And the initial value b is going to be 17.58 and some more decimals. So we can use those values and substitute them into slope-intercept form. So you can see we have those values here, and we're going to substitute those values and estimate them. We're rounding to the hundredths, that's okay. And now we have an equation for the best fit line. This is a linear equation that would represent the trend line that most closely matches these data points. If we were to graph this on a scatter plot, this line that we just substituted for A and B, that we used our calculator to find the linear regression, this equation would best go through all the data points. And we're going to use this equation to make predictions. This is our equation we use to make those predictions. Okay, just like we were doing in the previous lesson, our trend line helps us to predict other values. Try it number 1, use linear regression on your calculator to find the equation of best fit for this data set. So we're going to go back to our graphing calculator and enter these values again. X is L1 and the Y values are L2. So back to our graphing calculator, if we want to clear these lists, we can go up, arrow up to L1 and hit clear and then enter, and it will clear the whole list. So arrow over to L2 up to the top, hit clear and enter, it will clear the whole list. Okay, so entering the values for X from our table, 1, 2, 4, 5, 7, 8, and 9. Arrow over to list 2, 5.4, 6.1, 8.1, 8.5, 10.3, 10.9, and 11.5. Okay, make sure that you have the same number in each list. Hit the Stat button again, go over to Calc, and we're going to calculate number 4, the linear regression. Again, make sure your lists are pulling from the correct places. Enter, 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 hit calculate. There are your values for A and B. So from our calculator, we can write the equation in slope-intercept form, substitute the value for A, 0.78, we'll round to the hundredths place, X plus 4.69. Here is our best fit line. We can use this to make predictions. Example number 2, understanding correlation coefficient. So another value is this R value here. This is called a correlation coefficient. So correlation means they go together. Okay, things correlate, they match up pretty well, they go together. And we are talking about bivariate data, bi meaning two, variate meaning variables. So we have two variables. When we're dealing with y equals mx plus b, we have our variables x and y. And we can look at a correlation coefficient to see how strong the relationship is between those variables. How close do the data points fit that best fit line? So with correlation coefficients, we want to think like percentages. If the percentage is closer to 100, the better the data points fit that best fit line. The closer those data points are going to be to that trend line. You can think of it like a number line, okay? And 100% would be on the end or written as 1. And we could also have negative 1 because remember, we can have a positive relationship with a positive slope, and we can also have a negative relationship, a negative trend line with a negative slope. So as long as it is close to +1 or -1, we're going to have a really strong correlation coefficient. 0 in the middle, 0 correlation, 0% match between the data points and the best fit line or the trend line. So the closer you are to 1 or -1, the better the fit. Here you can see in this graph, our correlation coefficient was 0.984. That is very close to +1. It is positive because the slope of our trend line is positive. That is very close to 100%. That's 98.4%. That's a pretty good fit. So that means if we plug in these values into our best fit line, this would be a good way to predict other values for data points. When the correlation coefficient is close to 0, again, on that horizontal number line, 0 represents 0%, 0 correlation, 0 match between the data points and the trend line. So here we can see our correlation coefficient was negative 0.284. Negative makes sense because the slope of our trend line is negative, but those data points are not very close to that trend line. They're kind of spread far away from that best fit line. This does not look like it's a very good fit. And we can see from that value, it's closer to 0 than it is close to -1. So this is not a good fit. This line would not match the data very accurately. And again, here's a good correlation coefficient for a negative relationship. Okay, we have that negative slope. As x increases, y decreases. We can have a negative association. This is 99.5% of a match for that negative association. Try it number 2. What does each correlation coefficient reveal about the data? Okay, for part A, it's 0.1. That is a 10%. If we think of it like percentages, not a very good match. This is a weak correlation. Not a very good trend line. For part B, it's negative 0.6, so it is a negative association. So a negative relationship, and that's fine. That means our slope would be negative. And it's about halfway. It's a little bit past halfway, 60%. It's better than half, so we could say this was a medium strength or moderate strength relationship. Residuals. A residual is the difference between the value of the data set, the y value of the data set, and the corresponding y value that you would get from the best fit line or the predicted y value. So remember, we have our best fit line and we just figured out how to use our calculator to find the equation for that, y equals mx plus b, and we used our calculator to find that equation. Every y value on this trend line represents a predicted value. So the predicted values lie on the trend line, okay? So this is from the equation. The predicted values come from the equation, and the actual y values are coming from the data set. They come from the table. And all we do is we take the actual value and we subtract the predicted value and we get the difference. It's really just the distance between the actual data point and the trend line. That's what a residual is. How far away is it? And we'll have positive values if the actual value is above, or if the actual value is below, we could have a negative residual value. So you'll want to remember this equation. The residual is the actual y value, subtract the predicted y value that you get from the equation. And then we can plot the residuals. We'll take the original x values and plot the residual values, and we can do what's called a residual plot, and the x-axis is going to represent the trend line, and you can see the y-axis will represent the residual or the distance from that trend line, and they'll either be above the trend line or they will be below the trend line. And if your residual plot, after you've graphed the residuals, if it looks pretty scattered and randomly displaced, the data points for the residuals are randomly displaced above and below, we don't really see a clear pattern, then this tells you that the linear model, the linear equation, is a good fit because we want approximately the same number of data points above the trend line, and we want approximately the same number below the trend line. And we want them to be approximately the same total distance away. If I added up the distance above, it would, in a sense, cancel out the distance below. So this relationship is important. The residuals are not randomly distributed, then it would be some other pattern. So we're looking for random distribution that tells you it is linear. So let's try an example. Here we have a table. We have the year of flight school, and we have the number of students. And they gave us the trend line, the equation for the trend line here. So to find the predicted value, well, we're just going to plug in the x values and plug them into this equation. Okay, so for instance, we'll do y equals, for the first x value, it's 0 plus 1208. So that's how we get the predicted value of 1208. And then we would do it again, y equals negative 35 times 1 plus 1208, and we would get our next predicted value. So this is how we do our predictions. We get the predicted value by evaluating, plugging in x into the trend line equation. Okay, I'll do one more, y equals, we'll do this value for x equals 2 times 2, and if we do the calculations, plus 1208, our predicted y value would be 1,138. So that's how we get our predictions. They filled out the table for you, but you will need to be able to do the predicted values on your own. All you do is plug in x into your trend line equation. After we have plugged in our x values into the equation for the best fit line, and we've calculated our predicted values, now remember, we take the actual values. So the actual values are given in the table. We're going to take the actual values and subtract the predicted values. So we're just going to take this number given to us and subtract the value for y that we calculated using the equation. So we're just going to subtract, again, actual minus predicted. That will give us either positive values or negative values. So you can see here, that means this data point was above the trend line, and this negative one is below the trend line. So again, actual value minus predicted, and you can fill out your residual column in the table. Then we plot those residuals. So our x value is going to be our L1 again, and our y values will still come from L2, but there's a way that we can have the calculator pull from the residuals from our equation. So going into our stat edit, we'll type in our lists. Our list 1 will come from our x values, and our list 2 will come from our actual y values that are given in the table. Then we need to make sure we have the correct equation. So go to calc, let's do linear regression, okay, and have that equation saved in our calculator. Then go to our stat feature, so second y equals, to look at our graph. And we want to make sure that our y list is now coming from residuals instead of our L2 list. So to change that, you can do second and the stat button. You'll see that list option, second stat, and it pulls up this list of names. Number 7 is residual, so we want it to say residual. And then we can do zoom stat, and we can see here's our residual plot. The x-axis is our best fit line, and we can see that the residuals are scattered above and below. There's no clear pattern, so that means that our best fit line that we have saved from our data table is a good fit. The linear equation is a good fit for our data set that we have in L1 and L2. So again, we need to make sure our L1 and L2 have the data set for the number of years and the actual number of students. And then we did a linear regression to save the equation in the calculator. And then when we plot our graph, we just needed to make sure that our list 2 was pulling from the residuals. So we were showing a residual plot. And I like to do zoom stat if I'm using statistics with scatter plots, and it already has the correct zoom for the window. Here's a better picture of the residual plot, and you can see that those are scattered above and below. So this is a good fit for a linear equation. Try it number 3. The owner of Horizon Flight School also created a scatter plot and calculated the line of best fit according to this table, and here's her equation. So we're going to use this equation, remember, to find the predicted y values. We plug in x into there, and then we get the predicted y values. And then we'll need to find the residuals. So here's the best fit line she has, her equation for, just looking at it. There seem to be some far above and a couple below, but they're closer. So let's see if this equation actually is a good fit. So the actual values are given to us in the table. We're going to use our equation to calculate the predicted y values. Y equals 1.44 times 0 plus 877. That's going to obviously give us 877. Okay, and we keep going. Y equals 1.44 times 1 plus 877. And we will calculate and get a value of 878.44. And we can continue those calculations. I'm going to fill in the rest of the table, but you can continue calculating. Just input your x values into this equation to find your predicted y values. So after we've calculated the predicted y value using our equation, remember residuals are just the actual value minus the predicted value. So we can just line them up like this, and we're going to just subtract these two numbers. So the first residual I have to write over this, so I might have to go underneath. The first residual is going to be negative 45. 872 minus 878.44. This will also be negative 6.44. The rest of the residuals I will fill in. So again, you're subtracting actual minus predicted. So make sure you do the actual minus predicted so that you get the correct signs for each residual. And if we look, we have some below, some above. If we were to plot those, they would not be random or close to the x-axis. And you can kind of see it here in this original scatter plot. We do seem to form a pattern that does not look linear. So this equation, this linear equation, 1.44x plus 877, is not a good fit for this data set. It does not appear to be linear. Example 4. Here's another graphic showing regional air travel recorded by a domestic airline company. How can we use this data to estimate the number of air miles people flew in 2008? So if we look at this, 2008 is not in our data set, but we can use our best fit line, an equation for best fit, to make that prediction. Then we also want to make a prediction for how many miles people will fly in the future in the year 2030. That's going to be over here, far to the right on our data set. So first we can plot the points on our scatter plot. So again, our L1 will be the year since 1997. So this would be 0, this would be 3, etc. Okay. And then our L2 would be the miles. This is our actual value. Okay, so these data points given, the miles traveled would be our actual y values. So if we plug those into our lists, we would graph our scatter plot, and here you can see the scatter plot. And if we did the linear regression, remember you go to Stat, Calc, option number 4 for linear regression. We'll get this screen, and we're going to plug in these values for A and for B into our equation. So then our linear regression gives us this equation, 47.83x plus 2315.25. So here's our equation for the best fit line for this data set. Now to compute, to make our predictions, we're going to plug in these values. How many years since 1997 for these values, and then we're going to make predictions. So 2008, that is 11 years since 1997, so we're going to do x equals 11. And this, again, this data point would be inside our data set. So this is called an interpolation when it is within the data set. The prediction, the unknown value, is going to still fit inside our given data set. And if we plug in 11 into our best fit equation, we would get our predicted y value of 2,841.38 miles in the year 1997. Now for the year 2030, remember that data point is going to be far to the right. It is extrapolation. It's extra. It is beyond the data set. So we're making a prediction for something farther or outside of our data set. This is called extrapolation, but we do the same thing. We plug in the x value. The year 2030 is 33 years since 1997, so our x value is 33. And we do our calculations, and we can predict that people will travel 3,893 miles in the year 2030. So here on this slide, it just is summarizing what we did. We calculated these values, and is this reasonable? Does it seem that it's going to just continue to increase in air miles? Well, realistically, it doesn't seem that people are just going to travel more and more and more continuously in the future. So maybe this trend line is not going to be a reliable estimate because this trend might not continue. We're probably going to flatten out our trend line. People will probably stop increasing in travel, and they will just start to taper off, and that trend line would probably flatten out. Try it number 4, using this same model, estimate the number of miles people flew in 2012. So 2012, that is 15 years since 1997, so we're going to plug that into our equation. Y equals 47.83 times 15 plus 2,315.25. We do our calculations, and I'm going to round to a whole number, but we get approximately 3,032 miles in the year 2012. One more definition and term to go over is causation. Causation describes a cause and effect relationship between two variables. If one variable changes, that directly causes the change in the other variable. So if x changes, that makes y change, and it's the only thing that makes y change. So for causation, there are no other factors that lead to the change in y. Okay, so that's important. Causation, there is nothing else influencing the change in y values. Example 5, part A. A student found a positive correlation between the number of hours his classmates sleep and their test scores. So you can see here's hours of sleep, and the more sleep they get, the test score seems to improve. So we can see that positive correlation. Can he conclude that he will do well on the test if he goes to bed early? So we're comparing correlation to causation. Yes, we can see a correlation. We can see a relationship, but is the hours of sleep the only factor contributing to your test score? Well, no, there are other values that can contribute to your test score. Maybe you studied. Maybe you took really good notes. Maybe you understand the concept really well. So the hours of sleep is not the only factor contributing to your test score. So while there is correlation, there is not causation. Example B, a lifeguard notices that the outside temperature rises, the number of people coming to the beach increases. Okay, that makes sense. As it gets hotter, people want to go outside and go to the beach. We do see correlation. We see that positive correlation. We see a relationship between the temperature and the number of people at the beach. Does this mean temperature is the only cause for people going to the beach? Well, no, there could be other factors. Is it a break from school? Is it a holiday? Okay, so maybe more people go to the beach during fall break when it's not as hot, but there is a break from school or from work. So while there is correlation, there is a relationship, there is not causation. Temperature is not the only thing affecting the people at the beach. So it's very rare to have causation. Just keep that in mind. Don't just assume that if there is a relationship, if there is correlation, there is not necessarily going to be causation. Try at 5. The number of cars in a number of cities shows a positive correlation to the population of that city. Can it be inferred that an increase of cars in a city leads to an increase in population? So let's draw a rough graph of what this would be. Okay, and the number of cars is our x value, and our y value is the population. Does the number of cars, if the number of cars increases, does that directly affect the population? So it says we have a positive correlation, which would make sense. The number of cars would increase, probably correlates to more people in the city. But is the number of cars the only factor contributing to population? Well, no. What other things contribute to population? We could have births, we could have deaths, right? We could have immigration coming in, people moving to the city. So the number of cars is not the only factor affecting the population of a city. So while there is correlation, we cannot say that there is causation. We've made it to the concept summary for linear models, best fit lines, and residuals. So remember the steps to use your calculator to find the equation for the best fit line, that linear regression function on your calculator. And as you do that, you can then see the R values, or the correlation coefficient values, on your calculator also when you do the linear regression, and it will tell you how good of a fit that best fit line is. Representing it on a graph, we can see our trend line going through the data points, and then if we were to calculate the residuals, remember residual is the actual value for y minus the predicted y value that you get from your linear equation. So we would use this equation to find the predicted y value, and then we could graph those residuals. If the residuals are scattered above and below the x-axis, then that linear equation is a good model or a good fit for the data set. If you have any questions, put them in the comments and make sure to come back for topic 4.